I should mention that Bob is the co-author on these slides, so if they look good, it's because of him. But if they start changing behind me, I'd appreciate if someone would smack him and tell him to stop. OK, so I hope you took away from the keynote that there are a lot of very exciting things happening in Dart this year. There's all sorts of exciting things happening. But the one that I personally am most excited about, because I work on the language, is the fact that Dart 2 is happening. So I want to talk today a little bit about where we came from, how we got to this point of Dart 2, where we came from, where we are now, and a little bit about where we see the language going in the future. So I want to talk about a process of language evolution and how we've been managing that process over the past few years. So let's start with origins, our origins in the primordial slime, as it were. So the original vision for Dart, I think, was a very strong and very clear one. So sometime around 2011, there was this idea of making a new browser language, a new language, a better language for writing large web applications. So this was the vision of Dart, and I think it was a very strong one in a lot of ways. So the idea was to have a mostly dynamic language, layer over the top of that a sort of a lint-like type system that also provided you some runtime type checking, but still allowed you to be basically dynamic at the heart of it. So a mostly dynamic language running in the browser and running essentially over a just-in-time compiled environment. So one of the key ideas behind Dart, or one of the key properties of it, was that it was a language that was designed to be great on a JIT, without too much concern about making sure that the language was easy to compile ahead of time. So this is a very strong vision, I think. There was a lot to like about this, and we had a lot of success in getting some very large customers on there. So you already heard and saw an example of AdWords, people writing very, very large, very powerful applications and shipping them on the web, being very productive in the language, getting very good performance out the end, and basically being very happy customers for us. But things started to change over the time that we were developing Dart. So I think there was a very large shift in the model of how we were going to be delivering applications on mobile, as mobile became more and more important. And a decision was made not to put native Dart support in Chrome. So both of those facts changed the environment for Dart. So from a language which could rely on always running on a JITted platform, we were moving to a language where all of our important customers were shipping on ahead-of-time compiled platforms. So our web platform needed to rely on a compile to JavaScript story in order to ship their code. If we were going to compile to iOS, we needed to be able to do good, fast, ahead-of-time compilation. So we could no longer assume that we were always going to be running on a JIT where lots of interesting things are possible. So there was a sense that maybe the world was changing, and that maybe we needed to evolve with it, and we needed to think about how we needed to change going forward. I'll talk a bit today about what that process looked like. So one of the experiments that we did as we were doing this exploration was an idea we called strong mode. So the idea was, can we take this lint-like type system that's been layered over the sort of underlying dynamic language of Dart and tighten it up just a little bit, just enough to get a sort of a soundness property, to get the property that you as a programmer and I as a tool developer could both rely on the contracts specified by types to generate better code or to be more productive if I'm a developer. So this notion that we could use a stronger type system to get a good modular compiler generating good readable JavaScript very, very quickly, and at the same time maybe provide more value to our developers who are shipping very large apps. So we set out to do this experiment. And it was I think, a very interesting one. So we went off and we said, what do we need to build a modern type system that will support this? So there wasn't all that much we had to add. So we built in some type inference. We changed the subtyping rules a little bit, changed the override restrictions, basically did the things that we needed to do to make sure that you couldn't cheat the type system anymore, just enough. We built this prototype, and this I think is the most interesting part of the whole process for me, and the exciting part, and I think one of the reasons that this experiment was successful is that once we built this prototype, we didn't say, okay, we're done now, right? We didn't say, we've built this thing, here it is, take it. We had millions of lines of existing Dart code out there, and we just started throwing this at our prototype. So there was this very data-driven process of taking feedback from the actual code that people had written in Dart when it was a mostly dynamic language with a sort of a lint-like type system, and saying, what do we need to do in the type system to support the kind of code that people actually wrote? And there were a lot of changes we made to the type system over the course of this. The first iteration of our type system, we tried out using invariant generics, and we found there was just too much code out there that was using covariance. And so we said, all right, we went back to the drawing board and figured out how we could support covariant generics going forward. So this iterative process of figuring out what worked and what didn't work in supporting existing Dart code gave us insights into what a type system should look like for Dart. So I think there was a lot of evidence that this was successful. So certainly from a technical standpoint, the original goals that we set out to accomplish we showed they were feasible. So we were able to achieve a very fast modular compile and get a very good dev refresh cycle. So we were actually able to improve the refresh cycle for our web customers, even though we were moving to an ahead-of-time compiled scenario, which is very impressive. And at the same time, we were able to give better error checking through type inference and through sounder checking on the types. And so we had a lot of feedback from people that they really liked using this new type system, that it wasn't a huge burden, that it was actually a benefit. Interestingly, this was true even for people who were not getting the benefits of the new tooling that we were building based on this type system. So Flutter was one of our very early adopters on this, and they were simply using strong mode because they liked the better checking. So this was, I think, a very good indicator to us that we were on the right track. We were able to get better ahead-of-time compilation. We believed that this would carry over to mobile, to the native, and certainly we were seeing this on the web. So we had this evidence that we were able to take a language and make it great both for ahead-of-time compilation and for just-in-time compilation, get the best of both worlds, and get all the benefits of a sound type system without taking away all the fun things about Dart. So we felt this was really a great story, and the decision was made to adopt this as the core of Dart 2. So that's great. I think, so if you look at Dart 2 right now, the biggest change that is coming, and I think most of you have been working with strong mode, so you're pretty familiar with what the core of it is. The biggest change that is coming is this strong type system, this sound type system. But there's a lot of things that go into taking a prototype like that and making it actual real and making it usable. So there are changes to the tooling I think people are going to talk about. There's a huge amount of changes that needed to happen in the ecosystem. So many of you out there have been contributing so much to us as we've been migrating this forward. Thank you so much. At the same time, there are a lot of changes around the language and the libraries that we needed to make in order to make your experience with working with this sound type system great. And so I want to talk a little bit about what that looked like, what you should expect to see in Dart 2 from the language and the libraries that's going to make working with these things better and how you can take advantage of them. So I think when I think about the changes that we made to the language and the libraries around the edges of the sound type system, I think there are two key things we were trying to enable for our developers. And the first is we wanted to make it easy for you to stay statically typed. So any place where you were writing code and you had something which was nicely statically typed, and you wanted to do something to it, and you were having trouble preserving the types across that operation, that was a sign that we needed to add something to the language. And the second is we wanted to make sure that you were able to write APIs which worked great with type inference, so that if you're writing a library, the developers who use your library, your consumers, don't need to think as much about types. They can kind of continue to write their code just as they always have been, and they get a really nice experience while simultaneously getting all the benefits of the static typing. So I want to give a couple concrete examples of this to give an idea of how this played out in the language. So So this is kind of a core piece of the Dart API. This is a Dart1 API for the map function on iterable, on list, excuse me, iterable as well. So in Dart1, there's this map method on the list type. And the key thing I want you to notice about this is that the return type of the callback that you're mapping over the elements of this list is marked as dynamic. So there's no information about what the type of things coming out of it are. And the type of the iterable that you get out also has no information about what the type of its elements are. So it's an iterable of dynamic. A consequence of this is that code, like what I have written on the bottom there, is not going to be detected statically in Dart1. So you can take a list of strings, map something over it that tries to add 1 to it. There's nothing in the system that will tell you that that's a bad idea until it blows up at runtime. So we can fix this fairly easily without changing anything core in the language other than the type system in Dart2 by adding some type inference. So in Dart2, we added type inference so that that variable x in the callback no longer is interpreted as dynamic. It is now inferred to have type string, and we're able to give you an error here telling you, hey, this is not a good idea. You don't want to add 1 to a string, and you can fix your code. The problem is, this is still an error. This is still bad code in Dart2. And the reason is, as I mentioned before, this map function, this map method, doesn't give you enough information about how types flow from the inputs to the outputs. Right? So the return type of this whole operation is an iterable of dynamic. And in a sound type system, we can't allow you to put an iterable of dynamic in an iterable of string, right? Because in fact here, this is in fact has ints in it. And I can't let you put ints where strings are expected if I want to have a sound type system. The solution to this then was to change the language. So you are having trouble as a programmer preserving types across an API boundary. That means there's something in the language that is missing. So we added, very early on in the strong mode process, we realized we needed to add generic methods to Dart because it was the only way that we could preserve types across these API boundaries. So if you add this generic type parameter to map, now you are able to express the fact that the return type of the callback flows through and out to the result type and tells you exactly what the return type of the map should be. And so now you're able to write your code in a way that works in a sound type system. Even better, though, you don't have to actually write all of those types. So this gets to the second part. So this addition of generic methods is great because it allows you to preserve the types, but it's also great because it allows you as a library designer, or in this case us as core library designers, to express in the type of the method, in the API, exactly how inference should work with this. And therefore, you are able to leave, the developer at the end developer is able to leave all of the types off of their code just as if they were working in a dynamic language here, and we are able to fill in the types for them using this generic method schema that was laid out there. So these two ideas of preserving the type information and making the API friendly to inference play out very nicely here once you add generic methods to the language. So this is a big feature that we're adding to Dart2, and part of what we're doing is walking through the libraries and looking for where do these things need to happen. So another great example of this process is in the async APIs. So this at first looks extremely similar to the example that I just gave, right? So here we have the .then method on future, which is basically a map over futures. And in Dart1, as before, the callback that you passed in was typed to return dynamic, and it returned a future of some unknown type. And so you had the same problem with getting the information out the other side. So you say, OK, great. We have a solution to this. We make this method generic, and life is great, right? Generic methods for the win. And it does, in fact, solve this particular problem. So it's great. Generic methods got us a long way. And so when we first were going through this process of taking all this code out there and throwing it at our prototype, we added generic methods. We said, great, we've solved the problem, right? And we very quickly started discovering that, no, we hadn't solved all the problems. And async in particular was a place where we encountered something we had not expected and something that we would not have known about, that we would not have known to do if we had not gone through this data-driven process of trying to look at lots and lots of real code and understand what it was doing. So why is that? Well, the reason is that there's this very nice pattern that API designers were using in Dart. So they were basically taking this idea of dynamic and using dynamic as a kind of a union type. So they were saying in async code, I often want to be able to use the same code with async and non-async things. So before I was passing here a synchronous function to .then, so it's something that returns an integer, but I may want to use in the same place a callback which is async and therefore returns a future event. Well, that doesn't work anymore here, right? Because this generic method type that I gave says whatever the callback type is, I'm supposed to return a future of that, so this is going to be a future of future event. That doesn't match up. So when we looked at real code, when we went out and saw what people are doing, we saw something very reasonable that real developers were using that made a great API and which we couldn't type. And so that was a signal to us that we needed to go back to the drawing board and add something to the language. So this was something that was recently added to the language to make async code, which is a very pervasive pattern of code in Dart, great. So FutureOr is a new type in Dart, which has been added, which expresses this simple union type. So if you have a FutureOr of cat, that means either you have a cat or you have a future of cat. You can ask, so Dart allows you to check, am I a future or am I a cat? So you can tell at runtime, so the API inside of it can figure it out, and you can write all of your APIs to consume either one to be convenient for your developers. So now the right type for future.then, the one that actually captures the usage patterns of real programs, is to say that the callback doesn't return S, and it doesn't return future of S, it returns future of or S. It's allowed to return either one. And now you can use it very freely. I can call future.then with a synchronous function. I can call future.then with an asynchronous function. It all works. The types get passed through. And inference works out just great for you. Because again, we've incorporated into the type system an actual encoding of the developer's intent. So this is basically the theme, I think, of about the past year's work that we've spent on the language around the boundaries of this sound type system. So we added generic methods very early on. We added the FutureOr type to capture these patterns in asynchronous code. We've added the ability to use void as a first-class type, as a type argument, so that when you're working with code that returns, say, future of void, you can kind of continue to chain things through in a nice way, and inference can just propagate that void, and we can catch places where you might be using a void value unintentionally. Another sort of empirical thing we discovered was that a lot of places where people were writing dynamic code, it was because it was just too much of a pain to write, say, a function type. So you can always write a type def for a function type somewhere up, but if you just have some local variable and you're trying to put a function in it, it's kind of a nuisance to introduce this type def at the top level. So adding inline function types was something that helped us encourage people to make it easy for them to write strongly typed code. We also added null as a bottom. This is a fairly esoteric feature, but there are a few places where this enables some patterns that were hard to write otherwise. So the story here is basically about taking these new features that are designed to make working with sound mode great, strong mode great, and incorporating them into the libraries in a way that makes the developer experience great to work with. So that's all around the language. I want to talk a little bit about some of the changes we're making to the libraries for strong mode 2 and why we're doing what we're doing. So this is an example of something that you were able to do in Dart 1 that was harder to do in Dart 2. So I mentioned before that Dart 1 allowed you to use a list of dynamic. Dynamic was kind of a magic get out of jail card, right? So you could use a list of dynamic anywhere you would use anything else. So you could take this list of integers and strings and masquerade it as a list of integers. The type system would let you do that, and it is only if you actually kind of hit one of these strings unexpectedly that things would go wrong. We can't let you do that in Dart 2 because we want our tools to be able to rely on the fact that if you say it's a list event, it is. So you don't have to use the types in Dart 2, but if you use them, you can't lie about them. So that gets for the most part, that works out pretty well. But we did run into places where the libraries didn't have the functionality that they needed to allow you to write the code in the way that we thought you should be able to write it. And this is a very simple example. So suppose I have that mixed list again, and now I want to filter it down. I want to filter out everything which isn't an int, because I noticed that there is in fact a string in there, to get out an iterable event. Well, the first thing I can do is I can map a .where over that. This maps a predicate and filters out everything which doesn't satisfy the predicate. That's great, but unfortunately the return type of .where is still iterable of dynamics. So we're back in this situation of the static type system not being able to tell what it is that you want to pass in. So the fix, the workaround, was to map over it again, actually witnessing the fact that you've filtered things out. But this is really unpleasant. This is a workaround. So this was a clear sign that there was something missing in the APIs, and so we've been fixing that. So we've added to iterable a where type method, which will do the filter and return a new thing of the right type. It filters based on type. And so this allows you to write this relatively common pattern very cleanly and very concisely. So there's a number of additional methods and changes to the core libraries that you're going to see rolling out in Dart 2 that are designed around this idea of how do you make working with the core library types in strong mode very convenient, very clean, very terse, very Darty. So far I've all been talking about the work that we've done to make working with sound strong mode and the sound type system great. I've talked about how we've been updating the libraries. I haven't talked a lot about the tools, but you're going to hear a lot about that moving to the common front end. So there's a lot of work just around the type system. But there are a few more things coming in Dart 2 that I want to talk about. And one of the reasons I want to talk about them is they give us a little bit of a hint, I think, about where we see the evolution of the language happening in the future. So there are two things I want to talk about. I want to talk about 64-bit integers, and I want to talk about optional new and const. So in the original Dart vision, where we were living in a JIT-compiled world, it was a very natural choice to say we're going to make the native int, the native integer type, an arbitrary precision integer. So in the VM, you were able to add numbers together to your heart's content. You didn't have to worry about overflowing at 32 bits or 64 bits or 128 bits. As much memory as you had in your machine, if you waited long enough, you could eventually fill up that memory with an integer. And that works very nicely in a JIT, because the JIT, most of the time, you don't overflow. So the JIT just says, I'm going to just generate the code for the fast path, and I'll check for the error conditions, and if they ever happen, I'll bail out, and I'll recompile all this code and produce the worst case code. But most of the time, I'm in the small, compact, native platform code. Unfortunately, that doesn't work well on the web. So the web has always lived in the world where Dart integers are actually doubles. And unfortunately, it's a little bit too costly when we are compiling to native ahead of time. So when you are compiling ahead of time, you don't have the option of bailing out and regenerating the code. You have to generate all of that code ahead of time as part of the executable that gets shipped. So that means that your executable is bigger, it means your executable is slower, and that's a worse experience for our end users at the end of the day. So Dart 2 will have on native a default integer type of 64 bits only, and they will not overflow into big ints. This means we are able to ship smaller, faster code. So that's a benefit to our end users, but that's a big change for the language. It's not something that comes up very often, but it is something you need to be aware of as developers when you're working with Dart. The second big change that is happening in Dart 2, this was talked about a fair bit in the keynote, but is around this idea of reducing the amount of boilerplate and reducing the friction. So if you look at this piece of Flutter code here, there are a bunch of keywords which are really sort of redundant. So everyone in the world uses the standard coding conventions for naming constructors. So if you look at this code, it is completely obvious to you as a developer. There's very little additional information given to you by the fact that you say new, const, new, right? This is information that we can statically infer for you, and you as a developer can easily infer in your head just by reading it, just by looking at the names. So it really adds very little value to anybody. And so in Dart 2, we will infer these for you. You are welcome to write them if you want. but the system is able to fill them in for you. Edge insets has a const constructor. All of its arguments are const. Therefore, we will just make it const for you. Anything that can't be const, we will just fill in the news. So this is just this pattern of reducing the friction, making things lighter weight, making it easier for you to quickly get reliable code out the door. So if I look forward to where Dart is going to go, I think both of those two features there that I just pointed out give us an idea of where we want to see Dart going in the future. So there are two things that I think about. One is making our developers more productive. Okay, and I think of that as making Dart better. So I want you guys to be more productive so that you can ship better apps more quickly to the end user. And there are lots of things we can do to make Dart better. There are things like generic constructors that we don't have yet that allow us to take these relatively untyped constructors like from iterable and fill in more types on them. And again, this allows us to preserve types better, and this allows us to get better type inference so that the users of your APIs get a better experience. We'd like to improve the type promotion in Dart. So Dart already has a great feature where if you do an instance check on a variable, we will use that information to promote the type where possible so that you don't have to recast it or constantly recheck it. This is something we can make stronger and better, and that will reduce the amount of friction and boilerplate that you have to write. So this is something I think we already have a great proposal for from members of the team, and I really think we'll be moving forward on quickly. There's a bunch of longer-term stuff that we're looking at. As we get more and more users, it gets harder and harder to evolve the language. So I think we're going to be thinking very hard about what we need to add to the language to support further evolution of the language and library. We're very interested in maintaining this ability to work very cleanly with untyped and typed code. So I think we'll be thinking about how the language can support that very nicely. And there's a lot of interest. There's been a lot of interest for a long time, but there's a lot of interest in non-nullable types. This is a very hard thing for us to do because there's a lot of your code out there which is already written without non-nullable types, and so it's very hard to migrate that code. So we're going to have to be very thoughtful about how we do this if we do it in a way that doesn't break the world. But if we can do this, I think there's a lot of value we can provide to developers, both in terms of productivity by catching null errors, but also in terms of making Dart faster, which is the other thing that I think we're really excited about doing with the language going forward. We're very interested in continuing to push on this idea of making Dart a faster, better language for shipping native apps and web apps to end users. So we want to get the code size down smaller on web apps and on native apps, memory usage down, performance better, make better use of multi-core processors, whether that's through better isolates or other features, find ways to make the end user product a better experience by making the code that is produced by the Dart tools better. So this is something I think we're very excited about. The overarching theme here is that we want to make Dart the best language for writing client-side code. And I think we are committed to make that happen. So if I look back at the past sort of year or two of work, there's really an amazing amount of things we've done here. We've taken this very dynamic and fairly JIT-focused language, and we've migrated it, we've evolved it forward to being a fairly statically typed language that's very friendly to ahead-of-time compilation without eliminating the benefits of JIT compilation. We still have hot reload, we still have fast refresh cycles on native and on web. So we've been able to migrate this path of trying to keep the best of both worlds going by having a very data-driven process, using information we get by looking at the huge corpus of code that's out there and making sure that we fit what people are actually doing. When I look at what we have done so far, I look at it as we have produced a great platform for future evolution. We have set a baseline that I think we can use to continue to make the language better. And we are committed as a team to continuing to evolve the language. We are committed to growth. We are committed to making the language better. And we want to make Dart the best possible language for writing client-side code.